Are we not at Hogwarts? We're not. We're not! This is too much chem, and this is definitely too much, and I can't even figure it out. Oh well, okay. Welcome to Too Much Chem. I'm Johanna Brown. Today we are talking about intermolecular forces, which is something I see students struggle with a lot because there's vocabulary, and then there's a lot of understanding that needs to build up to intermolecular forces. So if you don't feel good about determining whether or not a molecule is polar, or even just thinking about molecular geometry and bond polarity, you should go back and watch those videos that came out just before this one. Perfect, right? So let's just start with the vocab to see what we're talking about and make sure that we understand what intermolecular forces actually are. So the first part is inter, and this is where people get confused because we have inter and intra, right? So if you've ever thought about anything that's international, it means it's between nations, between countries. So when we talk about inter, we're talking about across or between things. The next part of our word is molecular. Well, it's about molecules. So you should know that you're thinking about covalent compounds. That's what makes up molecules. So we're talking about across or between molecules. And the last part is forces. And people are like, oh yeah, force, totally. But remember, that's a push or a pull. And if we're going to overcome what's happening in this lesson today, that means that energy has to be put in to overcome that force. So intermolecular forces, you might also hear this as IMF, but I'll usually say intermolecular forces. Okay, so let's look at some molecules and see what we're talking about. Our first example here, we're going to start thinking about polarity and how that causes intermolecular forces. So this molecule here is hydrogen chloride. If you dissolve it in water, it's hydrochloric acid, but we're just going to talk about this molecule here. And for these example problems, when we discuss intermolecular forces, you need to think about the fact that it's not just a molecule in isolation, it's many molecules together, and you're thinking about how they affect each other. All right, so let's break down the polarity of this molecule. First of all, is it polar? Well, let's look at the electronegativity difference. Chlorine is very electronegative, hydrogen not so much, so we are going to end up getting that partial negative charge over there, that partial positive charge over here. So let's put in another hydrogen chloride molecule and think about how it would line up. So what kind of charge do you think is going to want to go by this partial negative charge? Well, you should be pretty good with Coulombic attraction. We're going to have a partial positive charge over here. So we'll see a hydrogen lined up over here, and then that bonded chlorine be over here. So we have that partial negative, partial positive, and we see that there are, I'm just going to draw squiggly lines to show that there's a force happening there due to charge, right? And here too. So if you think about all of those hydrogen chlorides together, they're going to stick to each other, right? There's a force here pulling them together. So this type of intermolecular force where you have what we call a permanent dipole that doesn't go away, that is just part of the molecule, these are called dipole interactions. Not dipole, but dipole. Because we have one dipole then attracted to another dipole, and that's why we're saying it twice. So don't let that confuse you too much. So if you have polar molecules, they're going to exhibit dipole-dipole intermolecular forces. Okay, let's get to our next one, water. So water is something we talk about a lot. In my other videos, we talked about why it was polar or not. Hopefully you've discussed cohesion before, how water really sticks up to itself. It beads up, it makes droplets. So we know that water is very attracted to itself, right? It's the Narcissus of chemistry. Okay, so water, is it polar? Well, yes, we already know that. We know that it's partially positive down here, partially negative up here. And the reason why I separated water out is because it's even more of an intense dipole than our hydrogen chloride. And this is for some very special reasons. Number one, oxygen is extremely electronegative. It's one of our top 3 most electronegative elements. So the electrons in these covalent bonds spend most of their time up with the oxygen. The other thing that's special about water is the hydrogen. So hydrogen is 1 proton and 1 electron when it's neutral, right? And so if this electron that hydrogen used to have with it is spending more time with the oxygen, all that's left down here is a proton. So it gets really, really positive. okay? So when oxygen and our hydrogens that are forming the water line up, we see a really intense intermolecular force happening here between the negative end of the water molecule and the very positive end of the water molecule. We call this, and don't let it freak you out, it's going to be a weird term, we call this hydrogen bonding. And it's not just because of the hydrogen, and it's not an actual bond. I'm sorry, it was named a long time ago. Let's break it down. This is the hydrogen bond right here, this attractive force happening here. It's because of a hydrogen being covalently bonded to a very electronegative element. This is not the hydrogen bond. That's just a plain old covalent bond. The attractive force happening here is the hydrogen bond. We see hydrogen bonding happening whenever hydrogen is bonded to our top three most electronegative elements, oxygen, nitrogen, and I hope you know the most electronegative of them all, fluorine. Okay? So that is when hydrogen bonding will happen. That's the strongest intermolecular force. Okay? So what if you have something that isn't polar? What do you do then? Can they actually stick together? Well, you should ask yourself, is there anything that's nonpolar that can be a liquid? Right? Because that's going to take some sort of force to hold it together in the liquid state at room temperature. We're going to talk about argon, for example, here. And we can actually see argon have intermolecular forces. And you might say, what? That seems nuts. That's a noble gas. It doesn't want to have anything to do with anybody else. But that's why it's the perfect example for our weakest type of intermolecular force. So let's look at what's happening with argon. I can't really draw out those complicated orbitals, but I want you to remember that argon has 18 electrons, and that electrons don't just sit and stay in one nice little space. They are constantly moving, they're constantly a particle and a wave and all that crazy stuff going on. So just to kind of simplify it, I'm going to just draw some electrons around our argon nucleus. We'll pretend that those are 18. And I want you to think, if they're all constantly in flux, that you might at some point get a buildup of electrons on one side, just by total chance, which would cause there to be a non-permanent dipole, a slightly negative charge where the electrons are built up, slightly positive charge where there are fewer electrons, right? Because we have protons over here. So we can have this non-permanent dipole, and then maybe if there's another argon over here, because it's negative right here, the electrons for this argon will move over to this side. Okay? And this is a bit of an oversimplification, but you can see how this impermanent dipole might induce some polarity on this argon and over again, and they're always changing. So if you have something that's nonpolar, it still has intermolecular forces no matter what. Because there are always electrons, they're always moving, and this is happening and changing constantly. You might hear this called, it's most commonly called a dispersion force. You might also hear it as a London force or a London dispersion force. Those all mean the same thing, and that's when we have these non-permanent dipoles because of the movement of electrons. So these are our three main. We have dipole-dipole with polar molecules, hydrogen bonding with polar molecules that have that special relationship between hydrogen and something really electronegative, and then we have our nonpolar molecules doing this weakest dispersion force. Okay. So the types of problems you're going to be expected to do is we will give you, most chemistry teachers will give you a molecule, and you need to tell us either all the intermolecular forces or maybe what the strongest one is when that molecule is being repeated, when there's a bunch of it in a container. So I've got some example problems here that we'll do to make sure we feel good on this. So here we have 3 example molecules. We're going to go through and determine the strongest intermolecular force. So you can pretty much assume that dispersion forces are happening across all of these because all of them have electrons. So let's see if there's anything stronger going on. Remember, we need to look at polarity to determine this. So first, let's look at formaldehyde. So do we have any polar bonds in here? Yes, that carbon-oxygen bond is polar. And then is it symmetrical? No, not like our carbon dioxide. There isn't anything balancing out this oxygen that's more electronegative. So we have a polar molecule. Do we have any hydrogen bonding? Is hydrogen bonded to the oxygen, nitrogen, or fluorine that we might see here? Well, no. So we have a polar molecule. That means that the strongest intermolecular force going on here is that dipole-dipole interaction. Okay, let's move on to methane. Let's look. Is this a polar molecule? No, there are no polar bonds. We've already talked about this. If nothing is polar, then you have dispersion forces going on here. That's the strongest one in methane. That actually kind of makes sense because we know methane is gaseous at room temperature, so it just doesn't stick to itself that well. Finally, let's look at ammonia over here. So, is this a polar molecule? Yes, it is. But go one step further. Do we see that hydrogen bonding could happen? Well, we have nitrogen bonded to a hydrogen. Nitrogen is very electronegative. It's one of our 3 most electronegative elements. So we would actually see the hydrogen be attracted to a nitrogen in another ammonia molecule down here somewhere. So right there, that's where the hydrogen bonding would occur, and that's our strongest intermolecular force. Hopefully some of those examples helped you out to make sure that you know what's going on. Just remember that it's across molecules and that we're talking about covalent compounds, and that it's really all about how well they stick together, which is due to charge. Thank you for watching. This is the end of season 1 of Too Much Chem. Be back for more this summer in season 2, and there are just a couple people I'd like to thank with this season ending. So you usually see me up in front of the camera, but this is truly the genius of Bjorn Knoblau. He is doing his senior project, and I think he's just done amazing. So he's done all the camera work, all the editing, all the marketing. Anyway, and then also support from Chris Reed, Ryan Curtis, and Charlie Jalapa, as well as teachers Mr. Luke Conley, who let me shoot in his room while my student teacher, Ms. Paige Latham, is teaching my class, our class, and of course Mr. Doug Winchell, our new media teacher at this awesome high school, who makes all of this possible. So thank you so much for watching, and we'll catch you next time. Cut!